Hello engineers. Today we are going to discuss on the topic characteristics impedance. Let us consider that the wave is traveling through a transmission line. The traveling will face some kind of intricacy due to the resistance and reactance part of the transmission line constants, and which is called characteristics impedance of the transmission line. The characteristics impedance can be measured from the propagation constant that is derived below. Have you seen a boat crossing river? It moves in a direction which is in accordance with the direction of the resultant of the water current and the wind direction, right? Now, this direction of the boat can be called as impedance. Similarly, if y is reactance and x-axis is resistance, then this line is impedance. Their resultant can be called as impedance. Like any other equation describing electrical phenomena, it comes from Maxwell's equation. That person was a genius, With practical approach, we can assume that the conductors are composed of an infinite series of two-port elementary components. Transmission line equivalent circuit. Each of the elements represents infinitely short segments of transmission line. dV by dx is equal to minus of r plus j omega L multiplied by I. This is equation 1, and equation 2 is di by dx is equal to minus of g plus j omega c multiplied by v. If we consider this triangle, the perpendicular axis is termed as x, that is reactance. The base of the triangle is RL, resistance, and hypotenuse is considered to be impedance ZL. If x is equal to xl is equal to j omega L and x is equal to xc is equal to minus of j by omega c, x will be xl is equal to xc. If r can be RL and RC, the ZL would be RL plus j omega L, that is ZC is equal to RC minus j by omega c. Differentiating equations 1 and 2 with respect to x, we get d square v by dx square is equal to minus of r plus j omega L dl by dx. This is equation 3. d square I by dx square is equal to minus of g plus j omega c dv by dx. This is equation 4. Now, substituting equation 1 and 2 in equation 3 and 4 respectively, we get d square v by dx square is equal to r plus j omega L g plus j omega c multiplied by v. This is equation 5. d square I by dx square is equal to g plus j omega c r plus j omega L multiplied by I. This is equation 6. In both the equation 5 and 6, it has the term r plus j omega L g plus j omega c. The r, L, g, c are the primary constants of the transmission line equivalent circuit, and this quantity is propagation constant gamma of the transmission line. Gamma square is equal to r plus j omega L g plus j omega c. This is equation 7, where gamma is alpha plus j beta, where alpha is attenuation constant and beta is phase constant. Now let us focus on a traveling wave. V xt is equal to V positive E minus gamma plus x plus V minus E minus gamma minus x, and this is the mathematical representation of a traveling wave, where x is the direction of propagation, where gamma is alpha plus j beta is equal to propagation constant, and alpha is attenuation constant and beta is phase constant. Now, what is attenuation constant? The real part of the propagation constant in any electromagnetic propagation medium is usually expressed as a numerical value per unit length. For each medium, it can be calculated or experimentally determined for each medium. For a particular propagation mode in an optical fiber, the real part of axial propagates on attenuation constant and the unit is Nepper per meter. Now what is phase constant? The phase constant shows how much a signal is shifted along the x-axis. A phase constant of psi says that each value of signal happens psi amount of time earlier. If the signal has a beginning, then a phase constant of psi means the signal occurs much earlier. The phase constant is significant when we have multiple signals because having different phases can cause destructive interference. The unit of phase constant is decibel per meter. Therefore, the characteristics equation of the transmission line V is equal to V plus E minus gamma x plus V minus E plus gamma x and I is equal to I plus E minus gamma x plus I minus of E plus gamma x are the transmission line equations. Now, differentiating the equations, we get d by dx V plus E minus of gamma x plus V minus E minus of gamma x is equal to minus R plus j omega L I plus E minus gamma x plus I minus E minus gamma x minus gamma V plus E minus of gamma x plus gamma V minus of E plus gamma x is equal to minus of R plus j omega L multiplied by I plus E minus gamma x plus I minus E minus gamma x. Now the coefficient of E minus gamma x equation LHS to RHS, we get E of minus gamma x is equal to minus of gamma V plus is equal to minus of R plus j omega L I plus, and the coefficient of E gamma x is equal to minus of gamma V minus is equal to minus of R plus j omega L I minus. Since gamma is equal to root over R plus j omega L multiplied by G plus j omega C, from equation 7 we can say V plus by I plus is equal to R plus j omega L by gamma and V minus by I minus is equal to minus of R plus j omega L by gamma. V by I is equal to impedance. Now putting the value of gamma in the equation, we get V plus by I plus is equal to R plus j omega L by whole root over R plus j omega L multiplied by G plus j omega C is equal to whole root over R plus j omega L by G plus j omega C, or V minus by I minus is equal to minus of R plus j omega L by a whole root over R plus j omega L multiplied by G plus j omega C is equal to minus of root over R plus j omega L by G plus j omega C. It can be easily found that the quantity whole root over R plus j omega L by G plus j omega C has the dimension of impedance and it is a primary constant of the functions of the operating line frequency. The line has a characteristics parameter, therefore it is known as characteristics impedance of the transmission line and generally denoted by Z0. Z0 is equal to root over R plus j omega L G plus j omega C. The parameters gamma and Z0 are known as the secondary parameters of the transmission line. Now that was all for characteristics impedance of transmission lines, and in this class we learned characteristics impedance, phase constant, attenuation constant. That was all you have studied about transmission lines, and this was the characteristics impedance of transmission lines. Watch the video again and try to understand the equations. If you feel you are missing out on the basic understanding of equation, then mail us. Which part are you missing out? Have a nice day. Bye bye.